All right, so this is going to be our first video on rotational dynamics. We're going to start off with torque. And so torque, well, let's go back to rotational motion for a second. So just like when we were doing rotational motion, we had ways of going between our rotational quantities and our linear quantities. So if you remember, if we wanted to go between one and the other, we said, okay, if we want to go between rotational and linear, we said, okay, our rotational analog is this angular displacement, and S would be our linear displacement. Just like that, we could say omega is our angular velocity, and velocity would be our linear velocity. And then we could do the same thing for acceleration. We could say alpha corresponds to our tangential or linear acceleration as well. And then we had some formulas that go back and forth between those. And that's sort of what we're going to do with torque here, because what torque really is if you think of linear displacement as the rotational analog of linear displacement, and if you think of angular velocity as the rotational analog for velocity, you can think of torque as the rotational analog of force. So think of torque as a push or a pull, as a force that would cause a rotation or a change in the state of motion of that object that's rotating. And so the way we represent that is we say this letter right here is tau. Well, let's rewrite it over here and I'll keep that up in that upper right corner. So we say tau, that's what represents torque, is equal to the radius perpendicular. I'll explain what that means in just a moment. But the radius perpendicular multiplied by the force applied. So for example, let's say that we have a bar right here, and it's going to rotate about this pivot point, which I'm going to draw a little dot to represent that. So it's going to rotate like this, or maybe like this. And we apply a force at the very edge of that bar. We apply a force like that. And so the force that we apply, in this case, it's perpendicular to the bar. And that's going to cause the object to rotate in a counterclockwise way like this. So what is the radius then? Well, the radius represents the distance between that pivot point and that force that you apply. So in this case, the radius would just be the entire length of the bar. That would be the radius right there. It's a little hard to see, but that's the radius right there. And so therefore, this force would cause it to rotate about a point. Well, what happens then? So why didn't I just draw a radius in there? Why did I say perpendicular to it? Well, what if your force isn't perpendicular? So what if your force is at an angle? And again, what I'll do actually is I'll give a brief explanation here of what torque is, and then I'll include some more detailed example problems and some solutions in another video. So for now, let's just think about this little bar right here, and let's just say if we had a torque that wasn't perpendicular to it. So what if we applied a force, I'm sorry, not a torque, a force that points like this? Now I hope that you can see that because the force is pointing at an angle, it's not going to cause a torque that's as great as if you did that force perpendicular to the arm, right? The perpendicular direction to the arm would cause the greatest rotation. Well, how much rotation then would you get out of this? Well, we have two new terms that we're going to introduce. The first one is called the line of action. The line of action represents the arrow that you would draw for the force and which way it points. So this right here is our line of action. It's which direction the force is pointing. We have another term that we're going to introduce, and this is going to be called the moment arm. This is this little dotted line I'm drawing in right here. The important point here and the moment arm is this R perpendicular. The important point is that the moment arm is perpendicular to the force that I'm applying. All right, so as you can see, if I were to look at this equation, the radius is no longer the distance from this pivot point to the end of the bar, right? The radius, the perpendicular radius, or the moment arm, is actually this distance right here. Now we need to know what angle is right here, right? In order to figure out what this perpendicular radius is, we need to figure out what angle that is there, and that would be given. You have to be given something to figure it out. But either way, we'll get into some more problems involving forces that are at angles. But this is the equation for it. It's the perpendicular part. You'll also see this written as the radius times the force times sine theta. Sine theta represents this angle right there that I drew. And so, well, okay, let's go back a little bit before we get to anything with angles. let's go back to our Newton's second law. So what Newton's second law says is it says that the net force is equal to mass times acceleration. Well, for right now, we're going to keep things simple, and we're not going to think about accelerations. We're going to think about static equilibrium, meaning the object is just stationary and it's in equilibrium. It's not going anywhere. And so if we had something that was in equilibrium and is not going anywhere, we would say our net force in Newton's second law is equal to 0. And we have a rotational analog for that. We say that the net torque, again, just like force, it's very similar to force. We say that the net torque then in static equilibrium is equal to 0. Now, of course, it's not always, right? We can have a force that does cause a rotation and it does cause an angular acceleration, and we'll get to that. And the equation that we would use, actually, I'll wait on that. But for now, we're going to look at things that are just in static equilibrium, that are not moving. Because when we do get to things that are moving, we get to moment of inertia, and that's down the line a little bit. So for now, we're going to say that the net torque is equal to 0. Well, just like the net force is equal to 0, doesn't necessarily mean that your force is 0, right? All it means is that your net force is 0, meaning all of your torques, when you add them all up, that equals 0. So you can have more than one torque on an object, just like you can have more than one force. For instance, if I have a bar right here, and I apply a force down like this, and then I apply another force up like this, I need to take into account the fact that both of those forces would cause a torque. Now the next question is okay, well, these are going in opposite directions. Which one's positive, which one's negative? It doesn't matter what you decide is positive and negative as long as you are consistent. My convention is a little different than I think what AP uses, although it doesn't matter. I'll stress that. It does not matter which one's positive, which one's negative. But my convention is something that would cause a clockwise rotation, I will consider as positive. Something that would cause a counterclockwise rotation, I will consider as negative. It's just easier for me to remember that. But again, it doesn't change the physics of the problem. It won't change the numbers that you'll get out of the problem. It's like when we're doing conservation of energy, right? So when we were doing those problems, it didn't matter if we chose one direction as positive, the other as negative, as long as you're consistent about that direction being that sign. And I will show you what I mean by that in just a moment. Okay, so I'm going to switch screens here. Oh, and then one last thing, which is the unit. What are the units here? Well, radius is a distance, and so therefore the unit for radius would be in meters. Force is measured in newtons, so this would be in Newton. Except for I wrote this backwards. It's usually newtons times meters, but it doesn't really matter, right? And so our unit here, it's nothing special. It's just a Newton times a meter. There's no special name for it. That's it. It's just a Newton times a meter. All right, so I'm going to screen share here, and I am going to bring up a little simulation that we have. This is a PhET simulation. And this PhET simulation, all right, so let's see if I can clear. Okay, so this PhET simulation, right here is this little triangle looking thing. That's what we call a fulcrum. It's the pivot point. And so if I take these two little balance things away, you can see that because there's an equal distribution of mass on either side, the fulcrum's right in the middle, it's not going to rotate. But if I were to put a 5 kilogram mass there, you can see it's going to rotate. And so what I'm going to do is I'm going to put a 5 kilogram mass right here. This is 2 meters away from the pivot point. So the radius of this object is 2. And then the force, of course, is just the weight of this 5 kilogram object. And so, actually, let me put the 10 kilogram one here. And so the question is where do we put a 5 kilogram object so that it balances this 10 kilogram object? I hope you can see that it has to be somewhere out here, but how far out, and how do we show that mathematically so we can figure it out for maybe a little more complicated case? Well, let's go back. All right, so what we have here is we have a little fulcrum. I'll draw it right over here. We have a fulcrum, and then we have a little balance beam right here. Here is our pivot point, and then we have an object of mass 10 kilograms, and then we have an object of mass 5 kilograms, and the question is where do we put it so that it balances out? All right, well, in that case then, I have 2 different torques, right? I have the torque due to this 10 kilogram one, which is going to want to rotate in this direction. And then I have a torque due to the 5 kilogram one, which is going to want it to rotate in this direction. So one of them has to be positive and one of them has to be negative. Which one is which? It doesn't matter. I'm going to keep with my convention, say that the 5 kilogram one would cause a clockwise rotation. The 10 kilogram would cause a counterclockwise rotation. And so therefore we know, because I want this object not to rotate, I want it to balance, the net torque is going to equal 0. And then we just add up the individual torques and then solve for what we want to, which in this case is the radius. So therefore we have 50. 50 represents the mass times gravity. Remember, that's our force for each one of these masses. 50 represents the mass times gravity of that 5 kilogram object, times the radius, what I'm looking for. I'm actually going to erase this right here. And then I'm going to put, just so this is very clear, I'm going to put this as R1 in case you can't see it. And this distance right here will be R2. And I'll put this as 5 kilograms. So R2 is this one that we're looking for. All right, so it's 50 times R2 minus 100, sorry. 100 times 2, which is what the radius R1 is. And then that's all equal to 0. We want to solve for R2, so I bring this over to the other side. So we're left with 50. R2 is equal to 200. And then you can see, divide both sides by 50, and you're left with R2 is equal to 4. What units are they? Well, it's your standard unit, so it's in meters. All right, so if the 10 kilogram object is at a distance of 2 meters, this should be at a distance of 4 meters. Let's go back to screen share. Okay, so I'm going to put, so if this is at 2 meters, 1, 2, this will be at 4. So it's 1, 2, 3, 4. So all the way almost at the very end. Okay, then I'll take the balance beams away. You can see it, they balance. And so there's no rotation here, so the equations worked out. So going back to my equations, you can see you have the same setup that you do for solving a problem involving forces, but now we have to add in that distance from the pivot point. I'll post a couple videos on some more complicated problems, but I think for a problem like I just showed you, I think Archimedes summed it up pretty well, which Archimedes said, to paraphrase him in probably a very inaccurate way, he said, give me a lever arm long enough and a place to stand and I can lift the earth. Meaning it doesn't, so if I were to go back here, I love that quote because it illustrates the point of torque very well. If I go back right here and I added, let's say, 100 million kilogram mass right here, right? In place of this 10 kilogram mass. Provided this arm right here, this arm is long enough, I can add in an arbitrarily small mass, provided this arm is long enough, right? As long as my torques balance out, I can lift up that object. In fact, I can raise it off the ground as long as that distance here, this radius, is long enough. And it has to be long enough according to our torque equation. So according to this equation right here. In fact, this gives rise to something called mechanical advantage, which is super important in physics, and I'll do some videos on that as well. All right.